Let us start this lecture with a thought process from Charles Dickens. Fan the sinking flame of hilarity with the wing of friendship and pass the rosy wine. You might be aware he is one of the great authors, Charles Dickens. So, in the last lecture we basically looked at flame extinction and its application, and later on we looked at also the flame quenching. Flame quenching is basically is one kind of extinction, flame extinction, and in the process also we defined the quenching diameter, and also we have defined the quenching distance, right. Generally quenching diameter related to a tube and quenching distance is related to two-dimensional burner or a kind of things. So, when you conduct experiment in both the apparatus, one is the let us say tube burner, other is a two-dimensional burner, or in the three-dimensional burner you can say, flame whatever you will be getting from a Bunsen tube, right, you will be getting three-dimensional flame, and when you get from the two-dimensional flame in a slot burner, right, that is known as slot burner, and that will be, there will be difference in the data, right. What I had shown you in the last lecture, the data about quenching diameter is related to three-dimensional flame. But if you conduct the experiment two-dimensional and find out the quenching distance, that will be different. So, generally the quenching diameter is around something 20 to 50% higher than the quenching distance. Why? Because the heat losses in the tube will be higher. Why? It is a curvature effect will be there, right. So, therefore, it will be much higher, surface area will be higher as compared to 2D. So, now we will be looking at a very simplified analysis to determine the quenching diameter, rather we will be relating that laminar burning velocity with the quenching diameter. So, we always talk about a quenching distance kind of thing, where the flame is entering into a tube. These are the wall. So, if you look at, this is the wall, right, of the tube, and this is if you look at, it is a basically tube kind of things. And the flame, this is my flame with having thickness of delta L, this is my flame, right. This is basically flame, this is my flame, right. And which is moving at a laminar burning velocity with SL, that means the burning velocity and particular mixture. Keep in mind that we are assuming it to be one dimensional, in real situation it need not to, okay, even inside. So, here we are assuming one dimensional. So, this is your Z direction and this is your R direction, and we are saying that at the center the temperature will be maximum, that is Tf, because heat loss whatever it will be passing through this, like heat losses, right, it will not be, the center may not affect, that is the assumption, otherwise it will be little lower. So, the temperature profile will be like that, and this is your Tu. Keep in mind that this will be asymptotically decreasing to Tu, but we will be doing some assumption in that. So, with this assumption, what we will do, we will basically look at the condition for flame propagation. Flame will be propagating provided the heat generated due to the chemical reaction in the flame is greater than the heat loss due to the heat transfer, and heat transfer can take place basically due to the radiation and due to the convection. But here we are talking about the wall, through the wall it is taking place. So, heat conduction which will be more important, because even though flame will be touching here, so therefore, it will be some kind of radiation also will be coming, convection will be coming, but once it will come to the wall, it is a heat conduction only, right. Of course, at the outer surface there might be some kind of radiation will be taking place, because temperature is higher, right. but we are not considering that. We will be basically considering the heat transfer due to conduction only, and this is a simplified analysis, therefore, we are taking that. So, for that the flame will be quenched when the heat generated due to chemical reaction will be less than the heat loss due to the heat transfer, right. That is the condition we will be applying, but in principle actually it should be that means the critical condition is what, when it is equal, right, we will be finding it critical condition, right. But if it is less, definitely the flame will be quenching. So, rate of heat generated per unit volume, like what it would be, it will basically Q dot triple dash is m dot F into delta SC is equal to Q dot conduction. This is my equation 1, right. And this is the condition, critical condition under which we are saying, look, flame will not propagate, because whatever the heat being released, it is being lost. So, will it, the flame will propagate? Flame will not propagate, right. So, that, and then that diameter in which it is taking place, we call it as a quenching diameter, right. And why we are considering diameter? Because that will dictate the heat loss. If the larger the diameter, then what will happen? The heat loss will not be that much, because the surface area will be not that big, but as it is smaller and smaller, the heat losses will be more, and the volume, the heat being released is reduced, right, and heat loss is increasing. So, therefore, we consider as a diameter. So, the heat generated in the flame volume, what it would be? It would be basically Q dot into m dot F delta SC into area. What is the area we are considering? Surface area. This is pi by 4 d square, this area, right, into the delta L. So, this is the surface area what we will be considering. If you look at like this is my flame, right, which is considering, this is the surface area what we are considering, and this area is pi by 4 dq square, right, and this is your nothing but your delta L. This is the flame in which is residing, this is my flame, rest of the things I am not considering, although there will be some losses, okay, but that we are not considering in the flame volume. So, heat loss due to the wall conduction, what it would be due to the heat conduction, wall heat conduction basically, it is Q dot conduction Kg into dt by dr, this is basically the surface area, pi dq into pi dq is the perimeter, right, into dl, that is the surface area, and this is the, right. Now, if you look at, if I will put this thing in equation 2 and equation 3 in equation 1, then I need to determine this dt by dr, right, which is quite difficult, because to at this condition I will be looking at here how much kind of wall it is. And the profile, if you look at, to find out this gradient at r, right, at different r, of course I can look at, but I will be more interested in here. How I will do that? We will be doing an approximation. What we will assume, that we will say this is basically, we will consider a linear temperature profile, right, because this is a non-linear, but however we will be considering linear, right, and then we will find out dt by dr Tf minus Tu and dq by C. If you look at C, when it is 2, like it will be linear, right. If C is equal to 2, then it will be linear kind of things, but otherwise if C pi will take something, it will be different, right. But however, this is an approximation. For to get this dt by dr, you will have to invoke the conservation of energy equation, and then you will have to solve it numerically or analytically and then do that, which is quite difficult. So, what we will be doing basically, we will substitute this let us say we will be substituting this equation 4, 3 and 2 in 1, right. I can get all those things. So, what we will be doing, we will be basically looking at this is that is Q dot due to the heat reaction, right, is equal to Q dot due to conduction. This is the thing what we need to put it. So, that let us say this is 5, I will substitute these values here, that is heat of reactions, heat generated in the flame volume is basically m dot triple dash F delta S C pi by 4 d q square delta L is equal to kg pi by dq delta L into T f minus T u dq by C. So, if I look at this delta S C, what is delta S C? Delta S C we know is equal to nu plus 1 C p T f minus T u, right. Are you getting? So, in that case what I will do, I will basically use substitute this here, in place of this I will be writing mu plus 1 C p T f minus T u, right. So, what is happening then? This is of course average, right, this is average. So, this pi will cancel it out, right, and this dq will cancel it out, this Tf and this will cancel it out, right. What else? This delta L also will cancel it out, right. Is it so? Delta L will be also cancel it out. So, if you do that, what you will get? You will get basically 4 dq is equal to 4 kg, right, and you will get 4 kg by nu plus 1 C p, right, you will get nu by C p. What else? Any other thing? Then m dot triple dash F 1 over that, right. C is coming, C will be in the up. So, this is C and this will be root over. Yes or no? C is a constant, you can see is basically a constant. This is some arbitrary we have taken, otherwise if I take as a linear profile I will take C as 2, right. So, after simplification, because we know that m dot F is basically 1 over 32 by 9 alpha by rho u nu plus 1 by S L square. I will substitute over here, right. If I will do that, what I will get? 4 kg we see nu plus 1 C p, right. I will get 32 by 9 alpha by rho u nu plus 1 S L square. So, if you look at nu plus, this will cancel it out, and this is right. So, I will get basically if I look at this, that I will get as root over 128 by 9, 32 into this, and kg by rho u Cp, right, rho u Cp is nothing but your alpha. So, I will get alpha by alpha square, I will get alpha square, I will be getting alpha by SL, right. So, but we know that what is your delta L? Delta L with the flame thickness is nothing but your 3 by 4 by 3 alpha by SL. C should come, okay, 128 by C, right. So, if I will substitute over here, right, alpha by SL is nothing but by 3 by 4, right, I will get this is nothing but your root over 8 C delta L. So, this is the relationship what you will get. That means, the quenching distance or quenching diameter in this case is proportional to the flame thickness. And the other things what you can see, there is another formula what we have just now see, that is dq is equal to 128 C by 9 root over dq is equal to root over 128 C by 9 alpha by SL. That means, the quenching distance or quenching diameter, rather sorry, the quenching diameter is inversely proportional to the laminar burning velocity. That means, burning velocity will be higher, what will happen to the quenching diameter? Quenching diameter will be small, right. So, therefore, if you look at, it is very difficult to quench the hydrogen air flame or hydrogen oxygen flame, because laminar burning velocity will be very high, and using this we can arrest the flame. Flame arrestor can be designed by using the quenching diameter calculation, right. For example, you are operating hydrogen oxygen or hydrogen air flame or methane air flame, you want to arrest the flame, what you have to do? You have to basically put some small tubes or a porous plugs or something that flame won't travel. And this is a similar thing what actually Humphrey Davy did without understanding much, like he could manage to do that, put a screen. We use a screen for arresting the flame. So, this small knowledge and also the relationship can be very useful designing the flame arresters. So, as I told that quenching diameter is basically proportional to the flame thickness. That means, the flame thickness will be higher, then what will happen? dq will be higher. If it is a smaller, then that will be the quenching diameter will be smaller. So, let us look at some experimental data for that. If you look at this is the flame thickness, right, and this is the quenching diameter, and this is versus equivalence ratio. If you look at, this is happening equivalence ratio 1 around on this range, right, there is a little shift, but it is having minimum quenching diameter, right. As you go towards the rich mixtures, right, and the lean mixtures, this is the lean side, this is the rich mixture side, that means the quenching diameter increases. Why? Laminar burning velocity is basically decreasing. So, because of fact that this dq is inversely proportional to basically alpha by SL. So, SL is decreasing, means dq will go up, right. And keep in mind that the your flame thickness is similar in nature. Flame thickness is increasing towards the both the rich and the lean mixtures, because we have seen delta L is proportional to alpha by SL, right. So, therefore, it is similar to that, the quenching diameter is similar to the flame thickness in. Okay. So, this is very important point what we need to look at it, and we will be in the next lecture we will be looking at flammability limits, right, and then we will stop over here. Okay, fine, thank you.